Good evening, everyone. Apologies for looking at me again. I did hand over my tenure as chairman last year, but Kate fell ill, unfortunately. She's a little bit sick, so you're stuck with me again for an introduction. I can see the sad faces. Thank you. But I think this time around, it's a very unique opportunity what we've got here tonight with Sarah being here. We spent the weekend with her in the Kruger, and it was quite amazing, you know, just to talk about other things than just engineering sometimes, and get to know Sarah a little bit better. But I think in terms of the introduction, I have to do the introduction, Sarah, and we're going to have some few people coming in. Sarah will understand now what I'm going to say, that there's a lot of people coming from Joburg, and they've missed the White Rocks. So they are completely veered off course. More than 2K. No, so we got to the lodge, and the ranger told us that you just need to go down this road, and you just follow the White Rocks. It needs to be on your left-hand side. As you follow it, you'll get to the lodge where you need to be. You just need to carry on. It's only 2 kilometers. So we were driving probably endlessly, I would say, after the White Rocks, and eventually I turned off, which I thought was a White Rock. Going back, I realized it was a glimmer of a quartzite that was just sitting there in the sun. But it was well trip. We went a little bit left, and we saw 2 hippos, and that was the start of the game drive. So then eventually we made our way back again. So no, it was a good start. So they are still looking for the White Rocks, but we as they come in. So don't mind them. We will not give them CPD points when they eventually. So the ones that are here, you'll get. So just on that note, there will be an attendance register that will go around. Just make sure you sign it for the CPD. And then I've arranged with Yolandi, sorry, my wife's name is Leandy, so I'm going to mix a few things. So I've arranged with Yolandi, if you want to go outside, the bathrooms are, if you go outside, she'll direct you. It depends on how you look. If you've got a phone in the hand, she'll direct you to outside. If you sort of go a little bit like this, she'll direct you to the bathroom. But probably let's get to the formalities. I want to get this going. So I think in terms of Sarah's biography, I'm not going to go through it, because you can go read up on how well accomplished one person can be. I think it's one of those biographies you read and you ask yourself, how is this even possible that a person can excel on so many levels and still maintain, you know, what you are maintaining currently, your stature, everything that you've achieved. I think it's something to aspire to for all of us. And I want to, in addition to all the engineering accolades, Sarah was the rector at ETH Zurich for 25 more years, 30? 7 years, yeah. Slowly but surely she moved to, Oxford 2 years ago. How many? Yeah, 4 years ago. Sorry, I got the bush wasn't good for my maths. She's now currently the principal at St. Hilda's College. But that's the engineering part started off at Cambridge, and you know, you can go read up on that. But the person that you don't know is the one that did triathlons all her life. She is a world-class triathlete. Very humble at that as well. She came 3 times. She came 5th in the Ironman, the Hawaii version, right? Twice. Won a few gold medals. She was the European champion. She is on the boards of all the triathlon unions that you can probably think of, Women in Triathlon, ITU, anything that you can think of triathlon-wise. She was also instrumental in getting triathlon as a sport into the Olympics. which is absolutely fantastic. It's something that obviously not many of us can say. I would probably put it that way. But more than that, you finished with your triathlons, and I read up a bit. That's the part that I really wanted to read up. She then went on, I think with all the running and the swimming and everything that went on, she said, I'll probably take a breather. And that was on a rowing machine and on a boat to row. So sat down, and then she started breaking records one after the other in rowing as well. And that's how, I assume that's how you met Rosie, right? Yeah. And the rest is history. She is absolutely accomplished on all fronts. I think it's very rare to have a person excel in their professional career as well as they did in their personal career, but then made a profession out of that as well. It is a very big honor for us to have you. I think your title, suction, saturation, and stability, those are probably the three main words in geotech engineering that we live by, that governs our profession in all aspects. And I'm not going to spend any time further to, Sarah, please come up and, give me a round of applause to welcome Sarah Springman.
Well, that was a bit over the top, Andre, I have to say. I did, on one occasion, I worked out how many seconds there were in my life to date, and when you look at it like that, I haven't done very much, so I think that's okay. It's been a huge honor to be invited to give this very distinguished lecture named after the South African father of soil mechanics, Professor Jennings, and I have many, many grateful thanks to SAICE. And what I want to try and do today is to consider lessons learned from field tests and field monitoring experiments carried out in Switzerland. And I'd like to explore some universal themes to explain and categorize responses of slopes to rainfall, and the effect of saturation, drainage, and effective stress on the mobilized soil strength are discussed together with the role of depth, permeability, and shape of the bedrock, as well as effects of vegetation. So I'm hoping that I can offer you some really simple models, almost back-of-the-envelope calculations, to those that are a bit more complex. Which you can see here. He was at WITS, and then he went to MIT for his master's, and then he went into practice, and we note a really broad base in research and practice, and then he became a lecturer, and then he went back to the university. And what I thought was so important for me, as a former rector who was interested in teaching, he had exceptional service in teaching and the training of young engineers. And I know there are young engineers in the room tonight, and you'll love to hear that. He also did original research on expansive clays, collapsible sands, and low-cost housing, foundations, and he was an active consultant in what we might also say a part of natural hazards, but very typical South African hazards. And I was thrilled to see, towards the end of his career, he was recognized by not one but two doctorates. So he was also a professional engineer, and he was very instrumental in forming SAICE. He was the president, he was an honorary fellow, he was given the gold medal, and he was a founding member of the International Society. And he also was an extremely responsible and thoughtful and visionary person who campaigned for effectively for the professional status of engineers. So good for him. He was really an amazing person. And I wondered, when I had a look at the 1953 conference proceedings from the third international conference that took place in Zurich, Switzerland. It was in our library, TTH, where I worked for 25 years, and he started some 44 years after this conference, in fact, was when I started there. And he did have a sole author publication in the proceedings. And I'm not sure whether he was there in person, but I like to think he probably was, as was Karl Terzaghi, amongst others. And then in my preparation, I found a very early collaboration between the now 90-year-old John Berlin, can you believe it? In 1962, he was a very young man, and he did his master's in this country. He was South African, in fact. And in a nutshell, they conducted odometer tests on selected saturated and unsaturated soils, identified a critical saturation degree for which Terzaghi's effective stress principle didn't work, and they then focused on volume change, but also said, oh, well, it'll probably work for shear as well. And then they said, practical significance is important, and I think both men had this as a feature of their careers. So that was quite an interesting little sideline here to find out about that. And I won't insist you read the paper, because I think if this had found its way into general practice, we'd be talking about it a bit more today. But still interesting that he was working on that. So inevitably saying, well, I'd like to come and talk about slope stability. Is it a problem in South Africa? Well, of course it is. We know that. But I was really happy to find some papers by Paige Green and a recent thesis by Rebecca Singh. And I had a look at lots of online materials and found a statistical analysis based on a landslide inventory data, which you can see on the right with the brown dots, and then put into data that was used in the modeling in the blue dots. And I thought that was really very interesting. You can see that actually where we were at the weekend, up here in Limpopo, clearly is challenging, KwaZulu here and also here in the south. So looking at Singh's work here, you can see the map for KwaZulu-Natal, and also I found this one for Limpopo, where you can again see lots of landslide activity. So I do have a reason to be here and to talk to you, although obviously there's been an enormous amount of excellent work done in your South African geotechnical world so far. I'm going to take a minor diversion and step back 45 years to the design and construction of an embankment dam. And such infrastructure assets that are engineered fills are assigned key specifications through compaction and where they're located to retain water and to allow flow through the granular media. And they rely on principles of effective stress and flow, and coincidentally, that accompanied me as a young engineer when I was responsible for the quality control of the 85-meter high earthen rockfill dam in Monosavu in Fiji in the early 80s. And curiously, I made observations from the stockpiles, which you can see on the right, of the almost axisymmetric natural stockpiles with water flowing through those stockpiles. And look at the shape, the concave shape of the slope, and hold that in your minds as I come on now to talk a little bit about landslides. So I want to go back now to Switzerland, where I spent 25 years, and I want to explain the country with respect to elevation and slope angle. And you can see the older Jura Mountains up here, which are running southwest to the north, and the younger Alps also in this direction here, running more or less parallel to that. And you can see in between them, in the green here, which is very low and very flat here, is the Mittelland. And the slopes are quite steep here in these mountains. You see when they're red, they must be rock, and in between, you'll have all sorts of mixtures of soil and rock and other combinations. And so we're going to bear that in mind now and have a look at the Swiss flood and landslide damage database. And you can see there are 3 levels of event: small circles, low, medium, and high, with the larger circles. And you can see that the floods are in blue, so mainly in the Mittelland and along the Rhone, and this is the Rhine rivers here, all the way around Lake Geneva. You can see the debris flows near the mountains here, and the valleys around the mountains, and the landslides are all over the shop, distributed across the whole country. So it is an issue. And of course, climate change has made it more and more prevalent. I'm going to go back to a single case of a storm in August 2005, which I think is a a really lovely example. And compared to 30-year averages, the month before August, July 2005, had very little rain. It was 10 to 30 millimeters less, whereas August was much wetter, about 70 millimeters more. And this is, on the left-hand side, this is a 48-hour record, and you can see on the right there are very small landslides in the brown and the much larger circles here showing they're up to 100,000 cubic meters. And so there was this huge storm flowing through the middle of Switzerland, causing all of this damage. This particular picture only shows superficial failures all around the small family farms. But I asked myself the question, what influences the initiation of failure? Why did it happen here rather than here? And why here rather than here, for example? And so slope angle is important, clearly. Soil type is important. The depth to bedrock is probably important, the permeability of the bedrock as well, and water flow and springs and slope drainage and all of those things. So we thought what we would do is we would carry out some field experiments. And so what I'm going to share with you this evening is what I've learned from a number of field and laboratory tests. The field test is a 38-degree steep instrumented slope. This is an in-situ shear box test carried out on moraine. We did large-scale triaxial tests also on moraine. And then we used all sorts of analytical models to try and interpret what was going on and when we were going to reach failure. Infinite slope and box slope failure mechanisms. We used the drum centrifuge, and we did some finite element analyses. And I'm going to talk you through some of those with respect to some of the different field tests that we did. And we also were very interested in what happens when bedrock is not parallel to the surface and encroaches quite near the surface. Does that cause problems and help us then to quantify vulnerability, establish risk, and ultimately protect infrastructure and lives? So I'm going to go back to this fairly old chestnut here. This is Guzzetti's status quo. How can we predict future storm intensities, the slopes that will be unstable? So you can see here, this is a double logarithmic plot of the intensity of the rainfall here in millimeters per hour against duration. And look at all of these particular sets of data. They're all over the shop. And given it's double logarithmic, it's really, really difficult to pin down which storm is going to cause a problem. And you have antecedent rainfall and a whole lot. So for me, this wasn't really terribly helpful. And I wanted to understand much better what would cause failure. So I had a look at some probabilistic predictions of rainfall-induced landslide design storms with different rainfall durations, intensities, whether the soil was completely wet or dry, the range of the soil depth, and statistically based soil parameters. And you can see there are 5 different versions of the map of Switzerland with lots of different colors. And blue and green are conditionally unstable, and unconditionally unstable slopes are in red. So you can see the different variations. And I'm going to present that to you in terms of the field tests that my group has carried out in the past. So the first one we did was on a moraine site in a place called Gruben. And then you can see that is in the south of Switzerland in the very unconditionally unstable conditionally unstable region. We then did 2 experiments next door to each other in the north, and these are in the zones that are apparently unconditionally stable to perhaps conditionally unstable. We went west and did a scree slope in Murecibak, which is also in the blue and red area also. And then we did some work on vegetation in the center of the country and also to the east of the country, which you can see again is in a mixture of zones. And so that really gave us a great set of field tests to be able to try and understand what causes landslides. And I'm going to talk to you now about the people, because actually I'm the professor and I'm allowed to stand here and talk about it, but it wouldn't be possible without the doctoral students. So Philippe was the first doctoral student, Andrea with Sven and Peter, who were postdocs, Amin and Francesca and Peter again, who were the postdocs, Daisy in the Mrechibek, and then Anil on the vegetation. So a quick tribute to them and my thanks to them for all of the hard work that they did. So I'm now going to come back to these useful plots here and show you again that Gruben is located here in the south, in the mountains, in the very steep slopes. So we're not surprised that's unconditionally stable. You can see the other two are on the edge of the Mittelland, but also quite close to the continuation of the Jura, interestingly. And then Daisy, again, her work in Mrechibek, also in the Alps, almost in state of incipient failure, her scree slope, and the vegetation in the middle of the country. So I quite like sometimes the idea of using slope angle to give me a first idea about how stable a slope might be. And we can see some data records of recent landslides in Switzerland from 1997 to 2005, plotted as a percentage of those landslides on the y-axis and the slope angle on the x-axis. And you can see they vary from about 16 degrees up to about 50. And there was one site that experienced similar storms in 2002 and 2005. That's this pinky one and the orangey one. And you can see they sort of not exactly the same, but there were some similar trends. And what one can pick up from all of this is that there are typical friction angles for granular soils, shown to you here in the gray, up to maybe high 30s if one's lucky, a bit of dilatancy. And here, these slopes here are only stable if you have some form of suction, vegetation, or cementation. And these ones down here probably had water flow or were slightly different, maybe not granular soil. So it was a very useful guide. It's not the only factor, but we're going to have a look as a small digression, as a thought experiment in very basic uncoupled soil mechanics. So, and I want to say this very clearly. It's very important to say friction is not fiction, whereby cohesion may be. And that is the source of lots of discussion, and I can tell you Imperial College in Cambridge have lots of fights on that. But anyway, I believe in the friction is not fiction, whereas cohesion may be. So if we have a reliable friction angle mobilized at large strain and shearing at constant volume, which you see is phi dashed CV, then the stress state in an element in a slope is shown in the black circle. But of course, often we'll have a situation out there in the field that the stress circle is much bigger than that. And we ask ourselves, how on earth is that stable? Well, a very simple way of looking at it is to say, well, maybe there's some cementation and I get a delta C dash for cementation. Maybe there's some root reinforcement and I get a delta C dashed R from the root reinforcement. And maybe there's some suction and I get a delta C star from the suction. And all of a sudden, the whole thing actually looks temporarily stable. But we ask ourselves the question, how reliable is the cohesion? And is it a function of strain? Is it a function of bond breakage? Or is it a function of saturation? So there is another way of looking at it, and this is something that Malcolm Bolton talks about a lot, when you could use dilatancy, psi. And instead of having a cohesion, you actually increase your angle of friction by adding the dilatancy. Again, that is a function of strain as well, but it is still another model that one can look at when you're doing back-of-the-envelope calculations, and I'll come back to this later on when I'm talking about the vegetation later on. So we all know this. If we have a dry granular slope with an angle of phi dash is equal to alpha, and so I call that alpha F1, and they represent the mobilized angle of friction, and it's jolly easy. You look at it and it's clear, as long as it's completely dry. So we then move on to the cases of and I'm going to assume it's a saturated granular slope, which of course it never is, and I'm going to give you 3 other cases, and compare the natural slopes on the left, the scree slopes in the Alps and stockpiles, and see they're remarkably similar. And so we can say that for the part of the slope where the flow is passing parallel to the slope, I'm calling it case 2 here, often alpha F2 is roughly half the angle of friction. Case 3 is at the bottom of the slope where the water is flowing horizontally, and F4 is at the top where it might even be flowing vertically. So here's a very simple picture, and it sort of reminded me of Carl Terzagh's emphasis on simple formulae, showing here a flow net with water flowing parallel to the slope, and you can see that in the standpipe that the water rises to the height of z squared cos squared alpha, I think, is that right? Z2 cos squared alpha. So you can see, and that feeds into the equation below, and that's really quite interesting. In the case for the horizontal flow, you can see here that the standpipe reaches all the way up through the depth of z, so you get a different equation, and when you put in phi dash of 35 degrees, your alpha F3 suddenly is a couple of degrees below alpha F2. And you can plot them up and compare them to each other and say, well, that's alpha F1, F2, F3, and perhaps partially saturated when you've got a suction, your slope might be stable at 45 degrees. So it's just playing with some thought experiments as to why all of those things happen in nature. So I want to now carry on with the interface between saturated and unsaturated flow. And let's consider now how the slope will saturate. And if you look at the picture on the left-hand side, you'll see where colored water has been allowed to infiltrate through a silty sand. And you can see that there are preferential flow through the root holes here. The bit that is blue is saturated, but there are odd bits on the side here and unsaturated sections. And where the water has got through to the bedrock at the bottom, it started to move horizontally across that. So that's one way of saturation, and probably means then that you will saturate your soil from the bottom up. The water will flow down and the water table will rise, and that will be interesting. What effect does that then have on the volume of debris? On the right-hand side, you can see the infiltration that only reaches to the surface, and you only lose the top skin and have a much lower volume of your landslide, but it might be more mobile because it is completely saturated, whereas on the left-hand side, quite a lot of this might be partially saturated. So the influence of pore pressure or suction on this mass here also affects how far it might run out. So we're going to come back to top-down or bottom-up saturation in the experiments that I'm going to be talking about later on. So I'm now taking you to the south. This is Philippe here, into the forefield of the Gruben Glacier. And we're now nearly 3,000 meters above sea level. You can see the Gruben Glacier coming down here, and there are lots of lakes, glacier lakes here, and you can see this is a moraine wall here with lots of erosion features that have led to overtopping and falling down into the debris flows, flowing down into the valley below and causing a lot of damage and sadly some deaths. So this work was really important to try and make sure that there wasn't a failure of that moraine dam, and in fact they constructed a very nice overflow weir, but to understand what the parameters were for this moraine. And it was astonishingly uniform in the way the moraine behaved. And in fact, Philippe's doctoral thesis was the one that, that sold the most of all of my doctoral students. And he was very proud of that too. So it was excellent. It was excellent work. So here we are now up on this moraine bastion, and you can see the slope is in the forefield of the Grubenklasse, and you can see the soil conditions are incredibly heterogeneous. You've got large boulders here, but you've got fine silt-size particles there that hold suctions. And we wanted to link saturation, water flow, slope stability, and debris volumes mobilized due to the rainfall. And we instrumented 2 slopes. This one was the 31 degrees the first year, 1999, and then the second year we added a second steeper slope as well. And we instrumented them with a number of instruments to determine volumetric water content, tensiometer. We tried to measure deformations. That was completely hopeless. Temperature and everything else, quite difficult above 3,000 meters above sea level. And the 31-degree slope didn't fail either in 99 or 2000, but the smaller area of 42 degrees did. And in trying to link together the slope angle and the strength, the critical state angle of friction of the moraine soil, we put sizes of particle up to 45 millimeters in a 250 millimeter diameter, 500 millimeter high triaxial test, and we conducted anisotropic, consolidated, drained, constant shear deviator stress. That's a long CADCSD, triaxial tests. And that was very helpful, and that delivered for us a phi-CV of 39 degrees, and then we did in situ shear box tests, and that came out as 41 degrees, and I'll show you the data for that a little bit later on. We installed a device called a moisture point, 1.2 meters long, and over 15 to 30 centimeter lengths. We were able to calculate what the degree of saturation was from the measurements, from the voltage obtained. And you can see at the very top of the moisture point device, you can see a very strong response here in the top 15 centimeters to rainfall here along the bottom. And this was, by the way, a 1 in 500 year storm, so we really rained on the slope. And you can see the response to saturation here, and then the rain stopped and it recovered, more rain, and we got up to just over 90% saturation degree. So the bottom line is, however hard we rain on it, it's probably never going to saturate completely, which was another insight for me as well. And you can see with each of the values down below here, down at the bottom, you had anything from 20 to 40% saturation. So it was quite clear the saturation was only really very close to the surface. And then the next year, what did we do here? And then the next year, we did it again, but only for 2 days. And you can see again on the top, we had the saturation degree here going up, raining for 2 days, went up to just about 90%. So similar at depths of 0.14 to 0.15 meters. And we actually this time, we managed to get some data from the tensiometers. And the suctions at the beginning were anything from about minus 20 to minus 35 kilopascals. And over the course of the rainfall, you can see the shallowest devices responded first and the deepest one last. But there was still 5 to 10 degrees of suction, 5 to 10 kilopascals of suction at the end. So if you do an infinite slope stability calculation, at the beginning of the experiment, you would say there was a factor of safety of 10, and at the end, there would be a factor of safety of 1.5 on this 31-degree slope. So it was still going to be safe. What happened on the 42-degree slope? Well, it failed after 2 days. So again, doing the calculations, it was probably about factor of safety of 7 at the beginning, steeper slope, but it was clearly 1 at the end. And there was a superficial slide about 20 centimeters of depth, and that was really quite dramatic and quite quick. So to summarize what was going on, taking the moisture point data and the TDR data over 1.2 meters depth. As it rained, you can see the soil saturating with depth, obviously saturating much more at the top of the slope, and you can see the suctions reducing with time. So as saturation degree went up, suction went down, and obviously the effective stress and the factors of safety also went down. So this is not rocket science. You all know this from your basic soil mechanics lectures. But it's still nice to see it happening, as it were, in the field. So I'd now like to show you our in-house direct shear box tests that we use for in situ testing. And we basically carved out a specimen and slid the bottom and the top part of the frame around it. And we had to do a little bit of backfilling with some mortar up to the middle. It required some very clever work from our technicians, I have to say, and they did it absolutely brilliantly. 25 centimeters square in plan. And it's described very well in Philip's thesis. Hope you can read German, but anybody who can read Afrikaans, I'm sure, can pretty much work that out, I'm sure. And we applied weights to represent sufficient normal stresses ranging from about 13 to 33 kilopascals. And when you normalize the shear stress against the ultimate shear stress tau u and plot it against delta x, which is the horizontal movement of the shear box, you can see remarkably similar traces for 5 tests on the moraine, which when excavated, weighed, and dried and graded post-test gave a saturation degree of approximately 50%. So quite convenient to be able to compare them against each other. And we wanted to compare or to determine the shear parameters, and particularly the C star, the suction cohesion, and to link saturation degree to mobilized shear strength. And here I'd really like to mention very valuable work from Professor Christina Yomi, who worked with Philippe and myself as we analyzed the large strain mobilized shear stress at failure. And it was plotted for natural specimens with average saturation degrees of 50%. That's in the blue, and the purple is 70%. And what's really interesting was that the angle of friction drawn through the 3 points for 50% was 41 degrees. We slightly cheated through the 2 points for 70%, but it did work out and look pretty good as being parallel to that. And the C star ranged from 10 for 50% to 2 for 70%. So we plotted that then on the right-hand side of saturation degree against a suction cohesion. We had a couple of other data points, and obviously that would be 0 at 100% saturation degree. And so we had a kind of relationship that was quite helpful for us for this moraine material. And I point out, just for a useful point, this is a very nice paper by Oberg and Salfers, which gives you another way of calculating the C star from the suction, the saturation degree, and tan phi dashed. Anyway, so combining very simple practical models, here the infinite slope analysis for a superficial failure, we can work out what a critical cohesion C star factor of safety is 1 as a function of unit weight, depth, slope, angle, and friction angle. And so then the question was, well, what friction angle should we use? This is the stress path. Oops, I've gone a bit exciting here. This is the stress paths here. So from isotropic consolidation and then moving up here, and then here increasing the pore pressure to fail the specimen here to give us the mu line. And so we had in the triaxial 39 degrees and again 41 degrees in the direct shear. So you can put those into the equation for C star crit, and you can work out that if you take 39 or 41, your cohesion that you need is about 0.1 or 0.2. And if you then look at this line here and you go up here for 95% saturation degree and you come down here and you see actually it agrees really, really quite well. So this might be a way of being able to do your calculations on how stable your slope is, depending on this suction cohesion. As we would say, bingo, it agrees really quite well. So that was Gruben. And we had top-down saturation through infiltration, in this case, in this moraine on the 31 and 42 degree slopes. The surface layer saturated quite well, but it limited the depth of failure really to a skin, and there wasn't such a large amount of volume of soil that failed. So that was the learning from the Gruben glacier experiment. So now moving up to the north, to Tusseg, and we're on the Rhine. And this is where they had 42 sufficient rainfall induced landslides in May 2002. They only had 10 centimeters of rainfall in 40 minutes, but there are some examples of the failures. And I was very familiar with this space because I used to train in my sculling boat up and down this part of the river. It was a very beautiful place to train, and then all of a sudden there were landslides. Oh, this is really interesting. And I could see a lot from the water. It was rather fun. So that's, of course, why we found these wonderful places to do our experiments. And we went here to Tusseg in the first case, and then later on we came to Rüdingen. But I want to talk about Tusseg first. And this turned out to be a 2-year field experiment to monitor, with the help of suitable measurement devices, the water distribution in the slope. And the farmer said to me, Professor Springman, auf Deutsch natürlich, don't you jolly well dare fail the slope, because I shall be very cross with you and I will come after you with my cows. And so I didn't like that idea very much. So we were very well behaved, and we put up a weather station. We had multiple rain devices, the thermometer, barometer, air, all of that stuff. We monitored soil temperature. We had a V-notch and a reservoir. We had piezometers at depth, and then we had tensiometer and TDR probes, and also volumetric water and volumetric other decagons to measure volumetric water content. So there's a lot of instrumentation on the slope, with 4 instrument clusters, 2 at the top and 2 at the bottom. And we just read everything over every 10 to 15 minutes over a period of 2 years, and got really a ton of very interesting data. The slope itself wasn't very big, but it was also not very steep. It was only 27 degrees, which was why I felt I could support the farmer in saying, well, it's all right, we won't fail it for you. And then we had to find out what was underneath that lovely, delicious grass. And we had an organic top layer, clay sand, silty sand, and sandstone. I'll show you the pictures here from, again, Peter Kienzler doing infiltration experiments with the blue dyed water. And when you take that away, you can see here where the dyed water infiltrated into the topsoil and really saturated it very well. You can see it pass through the clay sand, and probably in installing this tensiometer, you'd actually compacted the soil around it, so that wasn't probably very good either, was it? But there were other instruments in here, and down on the rock at the bottom, the water had spread out on the bottom. So quite interesting, preferential drainage paths and all the rest of it. And then we did a very thorough geophysical investigation. I must say that Sven Friedel, if you want to have a look at it, look at this paper here, because he did some really amazing work on actually chunking through the whole slope and working out where the layers were. I'm just showing you here the comparison of electrical resistivity tomograms taken in August 2003, which was very dry, showing very high resistivities on the surface, and this is obviously where the water is, lower resistivities. And then in the much wetter July of 2004, where you can see the water has been flowing down in this silty sand layer below the clay sand. And you might think, well, if this slope was steep enough, it might fail. But fortunately, the in situ, the angle of friction of the silty sand was higher than 27 degrees, and we didn't really get close to it at that stage. Now, this is quite a complicated picture. I'll explain a little bit of it, but there is a nice paper in Geotechnique that picks up on Andrea Thielen's work. And what you can see here over a period of 2 years, at depths of 15, 45, 90, and 150 centimeters, when you look in the, on this side here in the black, so all of these bits here, that's the suctions. And so here we are in the winter, there is not much suction, and the volumetric water content in the gray is very high. Again, this is the winter, and we lost some of the data there. And then you can see, this is the rainfall at the top, and you can see in the spring, it responds very much. So if it rains, the suctions drop off, the saturation goes up, and it gives you really a very nice picture of what's happening in the slope. And so that was quite helpful. And as a result of having all of this data, we were able then to do some analysis. Again, a very, very simple two-dimensional numerical modeling analysis, doing the finite element analysis of the flow and the suctions in the slope, and then carrying out very straightforward slip circle analysis. And so Andrea did quite a lot of work on water retention curves, saturation-dependent permeabilities, did some shear strength tests and so on. And at the end of it, she was able to come up with simple slip failures without accounting for suctions. The worst case in all of these 2 years was a factor of safety of 1.2, but when you accounted for the suctions, the minimum factor of safety was about 1.8. And so basically the contribution of the suctions became really, really clear, and this slope was never going to fail. So the farmer was very happy and remains my best friend. No, he doesn't really, but you know, it was all right. It was all right. So what we could see from all of this was that actually the summer regime, we had saturation from the top down, and in the winter regime, we had water flowing through the bottom in this silty sand layer here, and it was saturated up in the top. But what actually the soil saturation had an influence, but the slope was always going to be stable, frankly, unless uplift pressures developed in this deeper layer here, which didn't happen. And perhaps if you had a steeper slope, it would be more at risk. So that was a useful one to start off with in that region in the Rhine Valley. We then moved a little bit further upstream onto the orographic right bank, and to Rudlingen. And I was really, really keen that we should actually manage to fail a slope. And I wanted to instrument it and monitor it and bring it to failure safely. Please don't forget the word safely. There is one of our colleagues who very sadly had an awful experience with a landslide. I think it was in Japan. And not everybody came back alive. So this is something, when you're playing with something like this, you're not playing. You've got to be really, really careful. And this was something that weighed very heavily on me all the way through. So it's one of these interesting situations. We want to explore why a slope is stable. This was a 38 to 40 degree slope. You can see, you'd look at it and you say, yeah, it's all the vegetation, isn't it? Look at those trees. There's no way it's going to fail. But what you can see is, looking at this tree here, there has been creep in the slope, ladies and gentlemen. There has been creep, because the idea is that as the slope moves downhill, the tree always wants to grow vertically upwards towards the light. So we knew this was a slope that was quite close to failure. And we also wanted to find a space where we didn't have trees all the way up. This is a bit hopeful, about 10 meters by 35 meters. And we had a very interesting rock outcrop up here on the top right. And I'm going to come back to that a little bit later on because it's relevant. Now, the topological features along the Rhine River Graben indicate slope instability. Have a look at this feature here, and it's clearly slumping like mad here down towards the river. And there's a little road going along here, and there's a re-entrant coming up here. So, and we did ground and geophysical investigations, including dynamic probing, excavation of test pits, sampling, top of bedrock permeability tests, and that was very frightening when we poured water down and it all disappeared. So that explains also what happened a little bit later on. We did electrical resistance tomography, and we had a borehole. And the soil depth to bedrock was found to be variable between 1 to 5 meters, and then we had fissures in the horizontally layered bedrock in the underlying milestone here down at the bottom, which we hadn't really realized at the start. But when you go around the corner of this road here and you look here, you see this huge fissure. And when we started raining, there was an awful lot of water flowing out of that at the same time. So that was also quite interesting. We had rock here, sandstone above this horizon, milestone down below, and a couple of porous layers of bedrock here. And we built in 3 clusters of instruments. And I wanted to show you here this bit, the porous bedrock layers. Up here, you could see water flowing out in the winter and forming icicles. So that was a very good demonstration that these were porous bedrock layers here as well. So, and then we had sprinklers all the way down the slope. I'll show you that in a minute. And the bedrock also played an important role, because you can see there's this bump here, which I'm going to refer to later on as a sort of buttress, because that also has an influence on the stability. So this was the instrumentation we built into the slope. We had devices to measure volumetric water content, suctions, earth and water pressure, meteorological data, hydraulic measurement systems, and we also, this was a very Swiss landslide, ladies and gentlemen. Have a look at the steps up here, and in a minute you'll see we had lights, and that was also important, because guess what time the slope failed? We'll see that later, at 3:23 in the morning. So if we hadn't had lights, we wouldn't get the lovely films that I'm going to show you in a minute. So we videoed the surface movements and quantified them through photogrammetry, and we designed a novel instrument to try and measure the subslope deformations, which were manufactured and installed by our labs. Soil, always very important. What was it? So you can see it was the silty sand was a tiny bit of clay, 35% silt and 60% sand. We had some ESEM pictures, and it said we had smectite in the clay, but that didn't really seem to play any role at all. And in fact, we used a typical Rudlingen soil for all of our reconstituted lab tests, and also for our centrifuge tests later on. Excuse me. So I'm going to give you this. I'm going to give you this one to have a little look at while I have some water, and you will spot the field shear box data at the very low stresses giving extremely high mobilized shear stress. And you can see René, the technician, carving the specimen out. And of course, there was lots of suction, and there were probably roots in there as well. And then we went back and we reconstituted and did the tests in the lab. Those give us, in semi-unsaturated conditions, the blue dots, and then the other saturated ones. And at the end of the day, we had a phi dash of a critical state angle of about 31 degrees, which is a lot less than the slope angle of 38 degrees. So that gave us a lot of confidence that the slope really was going to fail if we managed to rain on it in the right way. We had lots of different doctoral students from different other professors. Massimiliano here Schwartz was very interested in the root reinforcement, and he did pull-out tests and root breakage tests, and came up with a picture of the C-R that he expected there to be in the slope. This was the shape of the slope here. You remember there were trees at the bottom and trees here. The brown are the tree trunks, and then the cohesion gets less the further away from the trunk. This area here, then, was the area that we would expect there to be a failure, so the top and the right. And as I said to you before, safety on site was essential, and so we had a very clear policy that if we had suctions of greater than 20 kilopascal, saturation degree less than 60%. Anybody could go anywhere. But the moment it went down less than 7%, 7 kilopascals, or saturation degree of greater than 75%, no one was allowed to go anywhere near the site, and not even on the road behind the net at the bottom. And the moral of the story is we're all alive today, and we had the failure, but nobody was damaged. And I think that's an important point to make. So we did 2 experiments, and the first one was in October, and we pumped 350 cubic meters of water in 4 days, and at an intensity of 10 to 40 millimeters per hour. You can see here the uniformly spaced sprinklers, which of course, Bernoulli means that we had more water coming in at the bottom. And you remember, we had the fissures at the bottom of the slope, didn't we? So it was a bit like trying to fill up the bath with the plug being out. And so, that's how I explain it in a simple way. So we learnt from this mistake, and we put lots of sprinklers up at the top of the slope the next time, and we got our failure in 15 hours, which was much earlier than I expected, I have to say, and it was only 65 cubic meters of water, 20 millimeters of rainfall at the top, and only about 7 at the bottom. So at 3:23 in the morning. So that was like, I'd just gone to put my head down, and they said, Sarah's failed. So I had to come rushing back, and you can see broken roots, and you can see pull out of roots here along the side. You can look at this shape. Isn't it a bit similar to what we said was going to happen? Doesn't it represent where there was much less root reinforcement? So it's not really very surprising. And our colleague Devrim Aksa did the most amazing work with the photogrammetry. And we can see here the erosion scar. Now, I want to try and show you some of the data before I show you the pictures. So what did the instruments tell us? We've got up here pore water pressure, we've got volumetric water content down here, and we've got the time of the saturation experiment for the second landslide experiment. And what you can see at the bottom here is that at the different depths here, there were suctions. And so there was a top-down saturation going on this left-hand side, and all of a sudden it caught up, and here the deeper one suddenly had more pore pressure, and here we are bottom-up saturation, and the water table was rising in that upper part of the slope, which was quite interesting, and you can see it sort of roughly mirrored in what happens with the volumetric water content. Here, this is the rainfall and the rainfall here. So we had a two-way system starting off with top down and then bottom up. So the water table built up, and this was in cluster 3 in the top level of the slope. So did we know that failure was about to happen? And I'd had an idea that it would be really interesting to design a deformation probe with a 4 centimeter wide and a 2 millimeter thick band that we could place wheatstone bridges on, 8 wheatstone bridges, and mortar it into the rock here and then measure the movements through the bending of this tool. Here's Armin here, and we had an inclinometer on the top, which actually was completely useless and didn't work, but we thought it might be at the time. And here's the data. We put in 4 of these deformation probes to a depth of about 2.5 meters. And I'm particularly interested in deformation probe 4, this one here, 2.5 meters here. And what you can see from the time here, and we had a shallow slip at the beginning at about 0.5 meter depth. And then gradually you can see it starting to catch up here until all of a sudden, woof, and we go from 3:15 in the morning and we're here, and all of a sudden at 3:25 and we're leaning over here, and the whole thing's basically had plastic strain and has gone well past its functional performance. So my hope that these might be useful for an early warning system was sadly put to death. But it was interesting to back analyze the data a little bit later on. So I'm now going to show you the first film. I hope I am. I'm going to show you the first film. To find it. It's at the bottom here, is it? Have I got the right one? I've got two different ones. I've got one that is yes, this is the right one, 1.5 minutes between the frames. And these are color pictures, and so you have to look very carefully. You can see the rainfall here. See the lights working beautifully. See the net down here at the bottom, very empty. And in a minute, you're going to see a crack up here. Boom, boom. Oh, dear. That's why in 1.5 minutes, if you were on that field, and you wouldn't have been able to get out of the way, would you? So you can see, again, all of this water that was escaping out of the back scarp. And I'm now going to show you it in a slower mode, where you have 0.23 of a second to be able to, between each of the frames. Now, I'm afraid this one's in black and white, but here we can see the development of the failure. So look up here, we're going to see a tension crack forming right at the top here, right at the top. It's suddenly going, there we go, it's moving away, shearing on the side and pulling out, shearing here, and then it gathers itself for 36 seconds, and then it accelerates for the last 12 seconds into the net at the bottom. And it was about a maximum speed of about 3 millimeters per second when it hit the net. So it was really fascinating to be able to see that and to be able to back analyze what was going on. Lots of people involved in it, lots of tributes to lots of people who helped us on the site. I'm just going to do one thing now and show you some centrifuge tests. This is for you. That's right. I thought, no, I have to show you a centrifuge test. So Armin and our technician team designed and constructed a climate chamber and a rain simulator based on Andy Take's work at Cambridge to test our hypotheses. And we studied the effect of the bedrock here. This is the bedrock parallel to the surface here, 2 meters of rock, lots of pore pressures, transducers here. And you can see we rained on this 1.27 millimeters per hour, and it sort of failed after 300 hours. When we installed here a buttress at the bottom, we got to 600 hours. And when we drained the bottom of the slope here, we got to 900 hours. So this is a very clear, practical example of how having a buttress system or having and especially combined with drainage, under drainage, can stabilize your slope. So these days, what they do sometimes in the Alps is they drive adits in under slow creeping landslides to drain the creeping mass so that it becomes much more stable. And I'm sure there are options in this country to do something the same. So in this case, the buttresses and the bedrock drainage prolonged the slope stability for the same rain intensity. So I thought that one's for you, Esfea. I thought you'd like that. So in summarizing what went on in this particular case, basically we had bottom-up saturation at the top with some minor top-down saturation at the surface, and we had exfiltration from the bedrock at the top and infiltration into the fissures at the bottom, and they were very much controlling the failure. And you could see there was a sort of semi-rotational translational flow in the upper slope, and we had lots of help from suctions and roots to aid stability, and we got some precursors of movement about 2 hours before the failure, but the deformation probe measurements didn't help us for early warning. But there are some useful points about remediation of slopes that you might find helpful. Now, the last major site experiment was Daisy's, and this is we're going to talk here a bit about the effect of bedrock on slope stability, even though she did lots of other lovely experiments. I'll show you the picture, it's all in the papers. This is a very interesting part of the valley, and this part of the valley, this Illgraben here, is the biggest debris flow catchment in the whole of Switzerland, and each year it delivers many thousands of cubic meters of debris into the Rhone at the bottom. Our site was just across here, The question was, thank goodness it's not doing the same thing, but why? And we had this little village down at the bottom that occasionally had some debris flows, and people were worried about the stability of the scree slope here and this active debris flow channel. And it was a 38 to 40 degrees again. There seems to be something common about that, doesn't it? And so Daisy was very interested, and of course we had the local fauna being very interested when we put some cameras up, and you can see how steep it was, and really was quite difficult to walk on. And she installed a number of test pits. She worked with a student to do some geophysical analysis. They did on the ground and also air, so from the air, to work out depth to rock. So that's all of these flights here and passes here, and she did her test pits in here as well. And this is basically the data, and I'm not going to dwell too long on this because it's far too complicated to take up in a couple of minutes, but rainfall down here at the bottom, temperature down here, so you can see this in the blue is winter around 0, and in the summer is the yellow bit. And so what we typically had was volumetric water content up here, so quite a lot of water around even in the summer, and then it got sort of locked in the winter somehow, and the temperatures were higher in the summer and then kept under a snow blanket to about 0 degrees in the winter. So quite interesting to see how one of these slopes responds. But I'm more interested, again, in centrifuge tests, for you, on the influence of steps in the bedrock on slope stability. So coming back to this 38-degree slope again here, with a depth of model scree on top, we had some very interesting geology that meant that the bedrock underneath had horizontal bedding, and then it had went parallel to the slope and came down. So we sort of approximated it like this, and we said that the height of this step as a function of h, so y over h, went from 0 up to, obviously not 1, to 0.8. And the length here, x2, went from a very long here to a very much shorter. And we did our sums on the amount of Q, the amount of water flow coming into the top of the slope, and what happened depending on whether you had a longer step, so you lost your stability much quicker with the longer step than you did with the shorter one. And we did some nice work in the centrifuge, and you can see again for the shorter steps here, shown with the simple slip circle analysis, or the slip failure analysis. You can see the water table climbing up onto the surface, forming a bit of a spring, and of course the failure was this green bit here, and you can see again failures happening in the centrifuge tests, and in the much longer ones here, you can see the failures happening all the way on the top of this bedrock here. And so I suppose my message here is that be careful what you wish for if you want buttresses, because sometimes it's not very helpful, and they can lead to earlier failure. So it does mean you need to understand what's going on below the surface. Right, so summarizing that last one, we had sufficient failures due to extreme rainfall or groundwater unlikely without significant changes in the slope, or events of great intensity and duration, no effect of vegetation, but the form of the bedrock was really important in terms of the length of the buttress and the height of the buttress. And again, poor old Agarn, the village below, was very happy to hear all of this information, and it fed into their analysis of the risk of the natural hazards. I'm now going to come on to just a last little learning about vegetation, which was Neil's work, and also some work from Armin, actually. So the first bit is about some centrifuge tests that Armin did. The contribution of the roots to the shear strength that was quantified using multi-stage direct shear tests and in a slope model in the centrifuge. He used cat grass. Anybody who's a cat lover, it's very important. Cat grass was very useful, called Avena sativa. I didn't know that till I did this experiment. And the roots were replanted in the reconstituted Rudlingen soil and tested on the same date to eliminate any time effects on the growth of the roots. And you can see here, this is what the roots looked like when they were excavated afterwards. And the vegetated slopes, either with or without a buttress, were stable during the entire 1800 hours of rainfall. And so the reinforcement due to the vegetation played a really significant role in stabilizing the slopes. And they were able to work out that they had a C-R of 2 kilopascal and a 1 degree increase in the phi-R. So that was quite helpful and is quite simple. We also did some really interesting work with Wei Wu and Barbara Svitala, his doctoral student from Boku, to validate a coupled hydromechanical numerical model with multiple hardening evolution of modified CAM clay, so that the P-C was a function of the saturated value, the unsaturated value, and the P-C of the root. So this is the consolidation of the mean effective stress of the yield locus on the P-dashed axis. And really interestingly, they were able to model Armin's tests, which are the ones with the solid line here, when there was an unload and then a reload here, unload and a reload here. I think it's reasonable representation, and we came to the conclusion that this model would be quite an interesting one for people to use if they wanted to analyze a vegetated slope. I'm now going to go on to Anil's work and to zoom out to the big picture, and I think this is something that you might find useful and be able to say, well, I agree with that or I don't. And we joined up with the WSL, which is the Wald, Schnee und Landschaft, which is a federal office in Switzerland. And we tried to quantify the effect of protection forests on the stability of slopes. So you can see up here behind, where we have forests, we don't have failures, but below the forests, you can see there were lots of failures happening. So what does that mean? And based on the work that Anil and his other supervisor, Frank Graf, worked on together with yours truly, we made a recommendation that slopes were stable to 5 degrees more in slope if they were properly vegetated with forests and without gaps in the forests above where the failures would occur. Well, certainly there was a gap up here, and that didn't seem to cause a problem, but basically you want to have continuous forest, and you can cope with having a steeper slope. And so we wanted to try and quantify the effect of the roots of grasses and shrubs, and we also inoculated, this is the royal we, they inoculated the roots with mycorrhizae as well. So this is the shearbox experiment, 500 by 500 millimeters square, with applied normal stresses of 6, 11, and 16 kilopascal, so very, very light superficial stresses. And they had lots of different types of plants. They grew them for 6 months and for 12 months under especially greenhouse conditions, and they inoculated as well, although I have to say the inoculations weren't terribly effective, but it was a very nice piece of work, and here is the data. So if you look at the left-hand picture, you can see that the phi-dashed constant volume or critical state of the soil alone was 34.3. So if we add the 5 degrees plus 5 degrees criterion to that, and then we look at the peak friction angles that were being mobilized in all of those tests, you can see that most of them came in above that plus 5 degree criterion, which was encouraging. He also plotted it as a function of the maximum dilatancy angle psi max, so defining that as phi dash CV plus psi max is equal to phi dash max, and again you can see there's only one that peaked in below that. So this is, we felt was probably also well supported, that it should be +5 degrees and not +4 or +6. And it certainly is something that is being used in practice in Switzerland at the moment. And I'd be very interested to hear if there's any equivalent in South Africa that people have any knowledge of. Although looking at this lovely meadow here, I'm not sure I've seen too much of those sort of meadows in South Africa. There's lots of rocks around very close to the surface. So you do have a rather different geology, and maybe that doesn't become quite as relevant. Who knows? I'm sure you'll ask me questions at the end. Just going to finish off with just a few other thoughts of other learnings. We did some very simple box-shaped limit equilibrium solution, where we could have, for Rüdlingen, we had a failure looking a bit like this. We could add suctions in the top here, and we could add the effect of root reinforcement. This particular one just shows an equation for that, dealing only with the suctions. And what it says is that where we have a suction of 3 kilopascal at a depth of 1.1 meters and a saturation degree of 50%, we will probably have a failure at that depth. And that was quite close to the 1.2 meters that we saw. But this is very approximate. I just pop it in here just to show you can do simple models. And actually what we did was some very interesting finite element analysis. Francesca Cassini did some very nice triaxial tests to failure, and she also did some water retention curves. And I realize it's a long evening and this is a bit complicated, so I'm not going to go into it in very, very, very great detail. But what she was able to find out from these water retention tests was that because of the sandy nature of the soil, once we got down to a suction of less than 10 kilopascal, there was a very quick rush to saturation. And all of this was fed into the finite element analyses, which again you can read about if you want to read the papers. This was Armin's work from his thesis in 2013, and he modeled the fissures in the bedrock here draining the slope. He modeled exfiltration from the bedrock here and got the failure surface that was not absolutely a perfect model but was quite close. He also did some three-dimensional analyses, which I thought was very brave of him, where he modeled exfiltration coming out here, so you can see high pore pressures on the surface. He also measured the drainage down here, but this really was quite difficult and not really very easy. So we moved on later on. Some very nice work done by Francesca Cassini with Panos Sitorenius, which actually won us the Stevenson Medal at the end. He did all sorts of interesting, complicated constitutive models, which Peter Day, you'll be delighted to hear. Sarah, don't show them these slides at the very end of your lecture. So he saved you from all of the slides, but they are in the paper if you want. These are very nice, this is the original modified cam clay is the grey one, but you can change this surface, you can tweak it in other directions, you can make it not normal, and you can deal with the state parameter as well. So if you're interested in that, do have a look at it. But I'm just going to show you some results, which I think is fair. He said I was allowed to show you some results. So here we go. So this is the slope here. And we've got on this side here, we've got the pore pressures at the bottom here, and showing at this point here that in the tensiometer here, we end up with suctions up to about 6 hours, and then we have positive pore pressures. And in the numerical experiment, again, similar level of suctions at the beginning, crossing over a bit later, but ending up more or less at the same amount afterwards. And a similar thing going on here on the top with the saturation degree, again, low saturation degree, and then saturating up here. The data are these green lines, and the numerical modeling is the smoother line. So again, giving us quite reasonable modeling. I was also told by Peter, oh, we like stress paths, he said, and SVS said I should show a stress path as well. So this is the stress path, and I've literally only got a couple more slides, so you can hold on. This is almost it. So what's happening here? We have a yield locus here. we start off at point A. This is the critical state line here. And you say, oh, look, it's jolly close to the critical state line, isn't it? Well, yes and no. Because what happens on the path is you have this huge yield locus here with the P0 is somewhere way out here. And as you move up to B, you come down to a lower value of P0. You come up to here and you come to a P0 dashed of 60, right, which is along here. And then as you shear to failure, you soften and the soil dilates as it comes down from C to D to E into F. And your final yield surface here has a P0 dashed at about 33 degrees at the bottom. So you're having a reduction of your yield locus all the way through as the soil is failing. And in the same way, you're coming up here, you're coming to the left along the unload-reload line, and then you're shearing and dilating to failure up onto the critical state line. We all love stress piles, don't we? It's quite fun. I always like them anyway. So it sort of explains to those of us who do look at stress piles occasionally what is going on. And of course, you can pick out every single point that you want to look at if it's interesting. And then this is the last slide of the results. So looking at the deformation and the failure mechanisms at, again, 14.5 hours. Very difficult to do this in a finite element analysis, but you've got the field data here and the finite element analysis picking up very well, no movement for 10 hours, and then suddenly increasing gradually and then accelerating and up here heading off towards failure. And I do commend the paper. It's a really nice piece of work. And Armin and I were very happy to join in and help Panos and Francesca to write all of that. So I have also done some work on what happens when the landslides flow, but I decided to spare you from that. You can look at Boyer and Neto Favero's data in the or work in the references if you like. So what contribution has been made to research and collaboration? I think we've had multidisciplinary research and cross-industry research programs that have had an impact at national and at EU level for the assessment and management of risk and to help make links towards policy making. I think the knowledge has been, for the assessment, the knowledge has been spread to multiple countries. There's a cost framework in the EU. Students come from all countries across that and we share, and it's absolutely fabulous. And we then develop valuable collaborations as well. So the technology and the knowledge transfer through education, what you're learning, education, research and innovation, go with the graduating undergraduates and the graduate students. And I'm going to say that loudly here because I know there are several of you here tonight. And through practical engineers engaging with CPD, which again I hear you're going to get CPD points for tonight. So I hope it was worth it in the end and you'll be able to say, yes, it was worthwhile coming. And in terms of methodology, what we can then say is that the natural hazard maps can then be developed at a cantonal level or at a regional level or at a provincial level, depending on how your country works, and it supports the design codes at national level. And I think those things are really very helpful. And we had a Swiss platform for natural hazards that I was lucky enough to serve on for a while, and was developing integral risk management across multiple hazards. And that has, again, fed into federal offices of environment, transport, energy, and communication, or supranational bodies in the UN program. So there's a huge thanks to all of the funding partners. I'm also going to say a huge thanks to, it's got stuck. I want to show the picture. Here we go. Huge thanks to all of the people. This was at the end of Rudlingen. We were absolutely exhausted, but you can see everybody's smiling pretty much. We had a lot of fun. And they're all saying, here we are. It failed. Lots of people who I have to say thank you to. And I always like to make the point that without the technicians, we would have been absolutely, this is a technical term, stuffed. And our electronic technician, Ernst, was the most important person in our team. Because without him, we wouldn't have got any of our data. So they were absolutely fantastic, and we worked with lots and lots of people. Thank you for that. And I'd like to say thank you to all of you, to Professor Jennings for his legacy to the SAICE, and I'm really happy to answer some questions if any of you feel you've got any energy to do that. Thank you very much. Sorry, that was a bit intense, everybody. You can ask me a question with South African relevance if you also prefer. This is going to be a difficult question, I can tell.
Nah, I'm too simple for that. Very interesting. Thank you for the great presentation. I noticed your vegetative slope, in fact, most of them are fairly shallow failures, not
Yes.
deep failures.
Yeah.
When it comes to the vegetation, there's always a dilemma planting trees on top. You get two pluses and a minus.
Yeah.
Evapotranspiration, root reinforcement,
Yep.
and the mass. On a deep circular failure, it's probably better to increase your resisting force by planting the trees in the bottom. Have you got any thoughts on that?
Well, it was interesting having a chat with Andre. Was it with you or was it with Mario about the weight of the trees? And I'm not sure that the weight of the trees is such a thing, because the bigger the trees, the larger the roots. And so, as you saw on that picture of the root reinforcement, you had a C-star reinforcement of, I don't know, Massimiliano gave it 80 kilopascal. And if you've got such a high root reinforcement, it ain't going anywhere. And I think the evapotranspiration is really good as well, because it keeps the slope in suction rather than allowing a water table to rise. So in my experience, it's worked quite well to have trees on the slope, although my experience up to now has been probably with saplings, which aren't terribly heavy, but are very hungry for water, and so suck it out and keep it nice and stable. And I think maybe if you end up by having very big trees, it may well be that you end up by lopping some of them down, so you have reduced load over an area, but you still have these hugely long roots underneath that are dewatering the slope. So I've not been so worried about the weight of the trees, I have to say. And wherever I've seen these forested areas, they really are a lot more stable than in an open slope. And in the open slope, you can see, as you said, shallow failures, typically not much more than a couple of meters of depth. So not a huge amount of debris to replace or to sort out. But it is irritating if you've got lots of failures suddenly in your grassland underneath the forests. So, but it is a fairly extreme rainfall event that leads to that, I'd say.
Yeah, thank you very much for your presentation. It's really interesting. I'm not sure if I missed a part where you mentioned about pull-out tests on the roots. So I wonder, how is that being done? And what can we use that sort of data and recommend for this slope at a certain angle, plant shrubs or sort of plants that can go how far deep? So that's
okay. So what they did was they had this shear box experiment that was working, and they measured the shear forces, and they measured they had obviously the normal stresses, and they were able then to work out what the values of shear stress was at peak and at large strain or large movements, and so they were able to calculate the mobilized angle of friction or the dilatancy. And out of all of that, they were able to see that when they had the roots there, it's really interesting that the effect of the roots pulling on the soil particles meant that in order to shear, the roots made the soil move up over itself. And so you ended up by having volume increase, i.e. you really did have dilatancy to overcome because of the intense network of roots. So these are grasses here. So these are small roots. They're not big tree roots. And so if you're in a forest, I think it's a different setup to if you're talking about grasses or shrubs, which are slightly bigger roots. But the effect of the tensioning the soil is very helpful in generating additional resistance. But of course, once you've strained past a certain level, your shear strength is going to drop off, and it ain't going to be there anymore. So you're going to end up coming to failure. But at least it doesn't start it, or it stops it moving up to a certain point. And so you can gain additional envelope of safety, if you like, by having vegetation. There's a lot of work now of people doing triaxial tests on vegetated samples, and so if you look in the literature, you can find quite a lot. But whether the grasses are the ones that you would have here or be relevant to South Africa, I'm not sure. But they're not terribly difficult experiments to do, actually, and you could work with your colleagues in biology or in SFER to grow specimens and do tests and whatever, if it was felt to be of any commercial value. Yeah.
Hi. Sorry, I'm not good at public speaking, so I'll try my best.
You'll be fine. Don't
No,
worry
I'm
about
sure it will be.
Just spit it out.
I'm curious with regard to your failures. They mostly seem to be shallow failures.
Yep.
So obviously, high water content. The water content plays quite a big role. There's quite a quick build-up, not a lot of volume for the water to be absorbed.
Yep.
So did you guys look at depth or ratio of slope length to soil depth to bedrock?
Okay.
And how that influences?
It's a very, very good question. So most of the failures that we were looking at, for example, in Turseg and Rudlingen, where there were 42 landslides in the after 40 minutes of rainfall, they were all pretty shallow. So typically you'll get a much deeper landslide where you've got creep going on and where you have a lot more happening at depth with the flow of water in a slope, and you might typically have a clay with residual planes and all of those things. So there are slopes that have deep failure surfaces that have so-called crises, which when the water table rises, they suddenly accelerate until the water table goes down again, and then they slow down again. And they never get to a state that they actually fail. But maybe at some stage in the future they might, and it could be a huge landslide. There's one in St. Moritz, for example, that has continued to shear down the slope over the height of about 1 kilometre, and it causes havoc on the boundaries of this failure, but it never yet failed. And so the kind of slips that I'm interested in and that come into the rainfall-induced failures typically are those that have a swift response to top-down infiltration or bottom-up infiltration, where you've got a transfer down to a rock base and then the water table rises. And if the slope is steep enough and the soil strength is low enough, and the pore pressure gets to a certain level and the effective stress drops, then you might have a failure. And it's all quite classic and also quite simple, actually, in that sense. What you're talking about for the deep landslides are really very complicated and need a lot more investigation and would be very heavily instrumented, I think, and would be much long-term failures that would have a lot of money being spent on them to make sure that the people living in the valley below aren't going to be damaged by them effectively. Everybody's a bit tired, I fear. Well, I'll be out there afterwards, so you can come and ask me if you prefer to ask me a question directly. Please do come and do so. Thank you.
Thank you, Sarah. This is a very small token of our appreciation. A proudly South African packet in a South African packet. So.
We've seen one of those. We've seen some of those.
Yep.
We've seen some of those. We haven't seen one of those yet.
No, yet. But they're very quick, so yeah. You have to watch carefully. But, no, thank you. No, thank you.